Hey guys, welcome. Yeah, so I hope everyone is doing well, and I hope the Lord Christ protects you all, and follow Him, pray to Him. He will protect you, I promise. And yeah, so while recently working with a student, a college student, preparing him for a multivariable calculus final, he shared this mock practice exam. And so for anyone who's interested in learning multivariable calculus, this is a really good practice exam to go through. As a matter of fact, this exam is a little too difficult. Uh, yeah, so if you're interested in a very rigorous multivariable calculus final, then this is one. Obviously, there's no need for you to read what's on this page. It's just the point allotments, right? And so, yeah, not very interesting. But let's move on and look at the first problem. Okay, so the first problem is actually pretty easy. So this is a question on Lagrange multipliers. Now, I already made two videos on Lagrange multipliers, but those are pretty advanced examples. And so, in fact, I really needed an easy Lagrange multipliers example, and this is going to serve that. So in this video, I'm going to show you how to solve this problem, and granted that you are watching this video series showing you the solution to this final. That is, granted that there is enough interest, I will show you how to solve the rest of the questions. But so that you know what is coming up, let's look at the second question. I did say this is a pretty hard final. And so here's the second, nope, yeah, it's page 3, sorry, but still the second question right there, right? So the second question, and this is about like volume, right? And so it's a volume of a sphere. So as you can imagine, it's probably helpful if we're in spherical coordinates, and so I'll show you a little bit of that while showing you how to solve this question, right? And if we keep it moving, we find arguably the hardest question on any multivariable calculus mock exam that I've ever seen, and that is this question. This is the so-called Laplace equation, but we have to show the Laplace equation in polar coordinates. My coordinates. Just kidding. Yeah, but yeah, we have to derive in this question the Laplace equation in polar coordinates. Now, if you try to do this in spherical coordinates, it's a nightmare. It's nearly impossible. But doing it in polar coordinates is pretty hard. In fact, I did not know how to do it, and so I looked through a number of resources, and all of them were really bad. I found one YouTube video, well, it's pretty popular. I looked at the most popular YouTube video, and it's terrible. The guy who solves it there, I think, is a professor. He does a terrible job because he doesn't really talk through the details. And of the online resources I found, this is like the closest thing to a good resource. There's like maybe one or two more longer resources. This is just 3 pages on, again, showing you how to solve problem 3. But there are too many details missing, and so you will not be able to like follow the argument here in this document. And so as there are too many details missing, granted again that you watch this video series and make it popular, I will show you how to solve problem 3. That is polar coordinate version of the Laplace equations, right? Okay, and problem 4, as you can see here, is on flux. And so given that you're benefiting from this video, then I will show you how to solve this question. It's a promise. Pinky promise. I promise. All right. And finally, here's an extra credit question on line integrals and multivariable calculus. And so path integrals, if you want to call them that, over a vector field. And so, whether or not you watch this video series, I will make videos about path integrals over a vector field, so lots of them to come soon, but I will invariably solve this if, again, you are finding this video useful. Okay, enough said. So let me show you how to solve the first question on this mock final. And the first question is, again, about Lagrange multipliers, and this was the question that we just saw on that mock final. Now, as I've already said, I have 2 videos on the method of Lagrange multipliers, but those videos are advanced examples. Example 2 is a pretty advanced example, and really between the 3, including this one, you really don't need another video to help you understand how the method of Lagrange multipliers works in execution, right? The big picture and the conceptual understanding, maybe that I will make another video on later. But yeah, this will be a nice first example. Now, in the second example, which is technically example 1 because we start with example 0 here. But yeah, in example 1, I showed you how to maximize the surface area of a rectangular prism. Remember, when we tried to do that in calculus, right, in regular calculus, not multivariable calculus, we had to assume that the rectangular prism had a square base. Because without that assumption, then surface area, even with a constraint function about the volume, would end up being a function of two variables. And of course, in single variable calculus, you don't know how to deal with maximizing and minimizing function of two variables. And that's where the method of Lagrange multipliers comes in. All it does is it helps you maximize a function of two or more variables. Now in this example, and in example 1 about the surface area of a rectangular prism, we're looking at a function of two variables. Example 2 shows you how to deal with a function of three variables. In fact, on a constraint where we have lesser or equal to, not strictly equal to. Of course, as you can imagine, when it's just equal to, it's easier. And so watch that example 2 if you want to see a much harder example, yeah? Okay, but let's commence. Enough said. Right? Okay, so the solution here goes like this. First, let's define a function g of xy, which is basically the constraint function all on one side set to equal 0. This is always the case. You need to define a function g of xy if you're a function of two variables, and g of xyz if you're a function of three variables. But in all of the situations, what you need to do to come up with this g function is you need to take the constraint function, whatever that may be in your situation, set it to equal 0, and the left side of equal to 0, right? The left side of that equation after you set the constraint equal to 0 will be the function g of xy or g of xyz, as I said, if you're in three dimensions or a function of three variables. All right. Okay, so where to from here? Well, from here we have two approaches, and both approaches are the same. They end up in the same place. The first approach, and perhaps like very standard on a lot of textbooks, is to write this together with the constraint function. Remember, the del operator, that's a vector, and so if you're a function of two variables, what this means is a two-dimensional vector where the first entry is the partial with respect to x, and the second entry is the partial with respect to y. Now, I have lots of videos on partial derivatives, so in this video, I'm not going to talk about the detail of how to find partial derivatives. Check out the other videos, yeah? And of course, on this side, we have the constant lambda, but also the del operator on this function g, and perhaps it should have been blue, forgive me. But yeah, just like the del operator on f, the del operator on g is a two-dimensional vector in this case, where the first entry is the partial with respect to x of g, and the second entry is the partial with respect to y of g. Yeah? Okay, cool. All right. The other option, right? I said two approaches. The other option is to construct this L function, what's called an augmented function. Yeah? And this L function is a function of three variables, x, y, and lambda, and it's constructed by taking whatever function is the f function and subtracting from it lambda, the variable here. Yes, I said lambda is a constant, but we'll end up taking a partial with respect to lambda if we construct this L function. So technically, lambda also can play the role of a variable if you go with this second approach. The first approach, again, is to take this equation together with the constraint function. The second approach is to construct this L function in this manner and use your imagination of how this L function would be constructed for a function of three variables, or watch example 2 and I show you how to do it there. But yeah, anyway, you construct this L function, right? And then after you construct this L function, what you do is find three partials of L and set them equal to 0. Of course, the partials for L, the three partials I just named, are going to be partial with respect to x, and then with respect to y, and then with respect to lambda. Yeah? And so when you set all three of the partials equal to 0, what you end up getting is the two equations from this plus that. That's why the two approaches are consistent or the same. Now, I will show you in action how exactly they end up in the same place using this example, but clearly in this example, the L function would have to be this minus lambda times this, because, well, our g function is right here. That's what I've got here. So lambda times g right there, right? Pointing you at the wrong spot. I meant here, right? And then this here is f of x comma y, right? Okay, and that you could see up there. All right. So where to from here? Well, as I said, we're going to go with, or maybe I didn't say, but I just said. So we're going to go with the L or the augmented function approach. And that's perhaps because of my bias and trying to triple major in math, econ, and stat in college. And so I got bored and abandoned the econ major as well as the stat major. Actually, only like about 2 courses each shy of a triple major. I just finished my math major. And part of why I was bored in my econ major is because we kept on just doing Lagrange multipliers in every single class. It felt like every class was about Lagrange multipliers. Obviously, economics is about maximizing and minimizing functions of multiple variables, but still, Jesus Christ. So yeah, my bias is that like in my econ classes in college, all we did is this augmented function approach. So for that reason, I will take the augmented function approach. And what I just wrote down, as I said, is well, we need to find 3 partials with respect to L, and so that's a partial with respect to x, partial with respect to y, and partial with respect to lambda, and set them all equal to 0. I've got 2 of them right now, right? The partial with respect to x, I'll just talk through that, and then, you know, again, I'm not going to talk about partial derivatives, but partial with respect to x of this, right, is going to be, well, this part is just going to be 3. This is a constant, so it turns into 0. And then you'll have minus lambda times, well, if you distribute this, it's minus lambda times x squared minus lambda times y squared, and then it's minus, well, plus lambda times 25, right? But then only the minus lambda times x squared will not be a constant when you're doing the partial with respect to x. The others are just constants, so they turn into 0. And when you do the partial with respect to x of minus lambda times x squared, what you're going to get is minus 2 lambda x, right? And so that's what we've got here, 3 minus 2 lambda x. Everything else is a constant. And then, as I said, set each of these partials equal to 0. Now, so far, I've just displayed the partial with respect to x and the partial with respect to y. This sounds very much like an infomercial, but so be it. This is what you get for like staying up all night and playing poker. Is like you get coffeeed up and start talking really fast. But anyway, partial with respect to lambda of like, yeah, of L, right, is going to be, well, this is a constant 0, this is a constant 0, right? And then here, lambda is the variable, right? I said lambda is a constant. Again, it acts like a variable when we define this L function. And so when you do the partial with respect to lambda of L, then again, these are constants, they turn into 0. And then this here is a constant because, well, it ain't got nothing to do about lambda, right? So you just retain the minus sign and this, right? Because what you've got is like minus constant times x, and then the derivative of that in single variable calculus would be like the constant, right? Okay. Where I'm calling lambda x the variable, right? And this is the constant together with that minus sign. Okay, enough said. I did say I'm not going to talk you through partial derivatives, and I already did a lot more talking about them than I should have. Okay, so why are the 2 approaches consistent? This together with the constraint function, and then these 3 partials will set to equal 0. This is why they're consistent, right? First, notice that this here, upon dividing by -1 on both sides of this equation and then adding the 25 over, turns into the constraint function, right? So the partial with respect to lambda equaling 0, that's just a constraint function. Remember, what I said is in the first approach, you take this equation together with the constraint. So we see how the constraint function comes up. Now, let's look at these guys. Okay, if we look at those guys, then this is what we're going to get. Well, first, del f equals lambda times del g, right? What is that going to be? As I said, the del operator is just taking partials of f with respect to x and y if you're a function of 2 variables. So, and then in this part for g, right? And so what we're going to get is a first equation from this here. 2 equations are really embedded in this when we're talking about 2 functions of 2 variables. And so the first equation is partial with respect to x of f is equal to lambda times partial with respect to x of g, right? Okay, but then now partial with respect to x of f, looking at f, is just going to be 3, right? Equals lambda times partial with respect to x of g, well, where is g? Right here, is going to be 2x. So 3 equals lambda times 2x. Okay, good. And then similarly, notice, by the way, before I move on too fast, look at this and notice that it's the same as setting the partial with respect to x of L equal to 0. Just add this term to the other side and yeah. Okay, and then partial with respect to y embedded in this is going to give us this equation, and notice that this equation is identical to setting the partial with respect to y of L equal to 0. Just add this over to the other side, and you'll see how they're the same. So, as I said, this here, which is this here, together with the constraint function, right, is the same as these three partials equal to 0, right? Okay, you see now why the two approaches are consistent, which is that they get to the same place. And again, just a reminder, the partial with respect to lambda of L set to equal 0 just gets us back the constraint function, right? Okay. All right, so now the three equations are, I've already written them, we're just rewriting them. So this, right, and that's this, and then or this if you want to think of it that way, and then this here, which is this, which is that, and then this here, which is this, which is, well, sorry guys, which is that. I'm sorry, too much coffee. I don't know if anyone heard it, but I like had a hiccup or something, or yeah. Anyway, what we're gonna do is, in these two equations, we're gonna solve for lambda, right? And so if we do, from the first equation, we get lambda is equal to 3 over 2x. From the second equation, we get 4 over 2y is equal to lambda, but then that simplifies to 2 over y, right? Now, this lambda and this lambda are the same lambda. In fact, they're yellow lambda. So they have to be equal. And since our objective is to maximize and minimize this function, what we need to do is figure out x's and y values that maximize and minimize it. And so we set these two lambdas to get to this equation about x and y. Oh, why do we care? Because, well, you see, the only unused equation from the three is the constraint equation. And what we're going to do is, well, we're going to get y in terms of x or x in terms of y, and then we're going to substitute in the constraint equation. That's me predicting the future, but here comes the future. So cross multiplying here, we can solve for y after writing this. That's a cross multiplying result, right? And solving for y will mean that we get y is equal to 4/3 x. Now we want y in terms of x because we like x. We want to keep x, right? We're so used to saying x. I have said x more times than you've said anything, like including all of your siblings and your aunts and cousins and everyone. Like I've said x more times than you've said anything. Okay, anyway, I don't mean the word anything. I mean like anything else at all. Like, okay. All right, so plugging into the constraint function, which is this, right? What we're going to plug in is 4/3 x for y right there, right? What we're going to get is this here. And, well, I'm going too fast because it's simple algebra that remains. First we get this, right? And then we get this, and then we get this. Well, how did I go from here to here? Obviously, I just squared in this part. And then from here to here, well, I just combined these two terms. This is 9 over 9x squared, and so that makes 25 over 9x squared when you couple these two, right? Okay, and then next, obviously, I'm going to divide by 25 on both sides of this very last equation. Doing that is going to get me that, and then I'm going to multiply by 9 on both sides, and I'm going to take the positive and negative square root, because you must do that when you take square root of both sides, right? And so I get this. So x has two values, plus or minus 3. Yes, I'm intentionally trying to talk as fast as I can. Alright, I'm trying to set a new record. So since we already said y is equal to 4/3 x, taking these two x's, we plug in right there, and what we're going to get is that, y is equal to 4/3, well, x. Okay, so when you simplify, what you're going to get is plus or minus 4 for y. We already had plus or minus 3 for x. And so there are technically 4 combinations you can make out of that, but it's pretty obvious that plus 3 and plus 4 for x and y respectively are going to maximize the function, and the maximal value is 25, and minus 3 and minus 4 respectively for x and y are going to minimize the function. Yeah, alright, cool. I hope you enjoyed this. As I said, there are 2 more advanced examples on Lagrange multipliers. If you give this video its deserved view, then I will solve the rest of this multivariable mock final. I might do it anyway because I love math, obviously. But yeah, like, earn it. Bye.